I guess we can begin today's morning session. The first speaker is Professor Yong-Geun Oh at Pohang University of Science and Technology, postdoc at Pohang, Korea, and he's going to talk about non-equilibrium, thermodynamic, information entropy, and contact geometry.
Okay, I'd like to thank Hyung-Gyu to invite me to give a talk here. But I feel that my talk is a little bit off the theme in this conference. At least, I mean, it is related to geometry and physics, but not algebra at all. So, but hopefully my talk will interest some of you. Okay, so actually the motivation for looking at this theme was that I got interested in contact Hamiltonian dynamics. And then I will try to find some core problems in this contact Hamiltonian dynamics because it's relatively new, but subject itself is very old, but nobody, and it has not been studied carefully. So, but I don't know what to actually study. And then I searched for the literature, and it turns out already starting from Gibbs and Herman, the contact geometry must be the geometric framework of thermodynamics. So I was very excited about it. And then I read those articles, and then I also got learned to know that, oh, there is a very interesting black hole thermodynamics in general relativity. And I look at some of those papers, I couldn't understand why. So one of the puzzles for me to understand was that why this entropy, black hole entropy, have anything to do with the area of so-called event horizon. And then it is my feeling that they seem to take some kind of analogy of some of the relation they discovered and to the classical thermodynamics. But I hope to understand how this interpretation really makes sense mathematically. So I started to go back and how the physicists derive thermodynamics from statistical mechanics. So thermodynamics should be the macroscopic revelation of this microscopic states in statistical mechanics. So that was the kind of beginning. And so let me start with the contact geometry. Maybe many of you may not be familiar with this. And it's contact Hamiltonian dynamics. So mathematically, the contact manifold is the pair. M is a smooth manifold. And psi is the contact distribution. So Coding-Measure the contact distributions, which is non-degenerate. What do I mean by non-degenerate? So this is hyperplane distributions. So there is some exact sequence, and psi and Tm and Tm psi 0. So you take some kind of curvature. So there is a natural curvature, a bracket operation from the section of psi to this vector section of this TM line bundle here. Okay? So if psi is the co-orientable, this is a trivial bundle. But in general, this is not. And so what this you regard this bracket operation, let me write this maybe the usual alpha. Let me write. So I'm going to write this non-degenerate bilinear form. This taking the bracket modulo psi. Okay? So if this is non-degenerate, that's called the contact distribution. If alpha is non-degenerate, and this psi is called contact distributions. Sorry, I'm a little bit too, maybe. So when psi is so-called co-orientable, then this is a trivial bundle. So in that case, we can choose a contact form lambda such that this corner of lambda is psi. Okay? And then this definition is equivalent to then d alpha is non-degenerate. Okay? D alpha. So we can choose such that d alpha is now two form. So d alpha restricted to psi is non-degenerate. Okay. Non-degenerate. So and then there is the, so in other words, this psi is maximally non-integrable. That's what. Okay, in other dimensions. Dimensional manifold M. Oh, yeah. So the example, of course, typical example is this. So you look at one-jet bundle. Let's say N is smooth manifold. And look at this one-jet bundle. This is the germ of these functions. This germ of function f is first germ of, okay, the n of R, this smooth, and this, let's say, x is the first one germ of one jet. I mean, one jet, okay? Germ of one jet at x. X is in it. Okay? And okay, this is, as a smooth manifold, is the same as Tm cross R. We know that this F one jet maps to dfx and fx provides that diffeomorphism. Usually one jet is written in this cotangent bundle times R. Okay? Yes? No, N is, oh yeah. Okay. M is always a contact manifold in this talk. Okay, and then what is the this contact distribution? In this case, this is always co-orientable. So we can choose canonical, the so-called contact form that is given by dg minus nj equal 1 of pj dqj. Okay, and pq, q1, qn, p1, Pn, the canonical coordinate cotangent bundle. Of this cotangent bundle. Okay. So that's a contact form, and then standard contact distribution of one-jet bundle is nothing but corner of lambda j. i.e., it's a subset of the vector field x and t okay, so what is it? Y? No, I don't like it. Okay, beta of J1n with it kills it. So in other words, the set of vector field that satisfy dz equal p and j equal 1 of dp j dq. Let me just simplify this, and then x vanish. Okay, that's what psi 0. Standard contact distribution. Pardon me? Alpha? Where is alpha? Oh, okay. This is the alpha. This bilinear form is I define alpha. So alpha is if you co-orientable here, just the contact form. Oh, not contact, it's curvature form. So this should be regarded as kind of curvature form. If you take a contact form as a connection form of this line bundle, and this is essentially the curvature, this bracket. Okay? So that's why this non-integrability have something to do with this curvature of a line bundle. But okay, is that clear? So in 3 dimensions, and it is the contact form is just PDQ. Yes?
We're talking about the jets. If you can just say it's star n cross r. It was forget about K1.
Yeah, you can, but it has one jet bundle is coordinate-free object, a jet bundle. It has nothing to do with that splitting. That splitting itself is sort of not not canonical. Is it? Yeah, I think not canonical. A one jet bundle, okay, you look at the space of one jet, that means the value of 0 and up to, if you take the Taylor expansion, we are looking at up to order 1. So if you choose a different coordinates, probably it's a canonical. But the D coordinate, is it canonically defined? One jet. the value. Okay. Value and then differential up to 1z. Maybe that's not canonical. Oh, 1z. You look at space of functions, smooth function up to 1z. Maybe the symbol, there's something to this. Or maybe first order differential operator. So the symbol is coordinate independent. Value is independent. Yeah, maybe this is canonical. Okay. So you can think of 1z bundle as this product. No, alpha is a two form. Sorry, I should write curvature. Well, okay. It's a notation. Just. Oh, sorry. No. This is alpha is two form, not three form. Oh, D lambda. Oh, I'm sorry.
It's still canonical in the sense that it's part that's built off of Louisville. Yes.
Which one?
You're using the Louisville form.
Yeah. I mean, this should be written to precisely dz minus 2 back of Liouville 1 form. So I think it is the value, when you give 1z up to your value is natural projection, so it maybe it's the canonical.
So we can forget K1?
Yeah, you can forget, but in some cases, it is more natural to regard this as a 1z instead of taking the product. Okay, so this is QPZ. This is the three-dimensional case. Maybe I'll use QPZ. Yeah, okay. So the distribution is when this is Q, maybe PZ. Okay. So what happened? PQZ, PZQ. Okay, that's okay. So when P equals 0, that one form is just DG. So the kernel is just DG. So this, right? The kernel is DG. So the PQ plane here, when P is a kind of slope. So Q here is a QZ. And when P is 0, the slope is 0. So that means the contact distribution is here. And then it slowly rotates. If P becomes go positive, this plane rotates, but it cannot rotate completely. As P, let's say, going to infinity, the slope becomes infinity. That means it's vertical. So this contact plane slowly rotates as you P go to infinity. It's okay. So this kind of structure, it has that property. But you can imagine the kind of structure, this contact plane rotates more than 20. And sometimes, right? That sort of classifies how the two contact structure could be different. So in fact, that is the important criterion for classification of or between so-called over-twisted and tight contact structure in 3 dimensions. Okay, now this is geometry. Now if you, by definition, now let's Now from now on, oh, one more definition. And in symplectic geometry, the most important geometric object is so-called Lagrangian submanifold. And there is a similar object called the Legendrian submanifold. And this is, the definition is the maximally integrable submanifold. So this submanifold S inside contact distribution is called Legendrian if S is maximally integrable and so that means maximal integrability implies the dimension of S should be the n when dimension of m is 2n plus 1. Okay? So in symplectic geometry, the Lagrangian submanifold has precisely the 1/2 of the dimension of ambient manifold. So the intersection theory makes sense because they have any pair of Lagrangian submanifold are complementary dimension. So this intersection theory is the crucial information for the symplectic topology. But if you look at the Legendrian submanifold, as I said, the dimension is n, but inside the dimension of ambient manifold of dimension 2n plus 1. So the intersection theory does not make any sense. Generically, they do not intersect. But you can think of so-called linking, or so a geometric informations or topological information is encoded in their linking property. Okay? But this is geometry, some kind of kinematics. Now we are trying to turn on the Hamiltonian flow, Hamiltonian. So what is the contact Hamiltonian? Hamiltonian flows or dynamics. So in symplectic case and contact, and here symplectic bilinear form is given, but in the contact geometries, the given data is a contact distribution. And in symplectic case, whenever you are given these functions, this generates some vector field, which is called Hamiltonian vector field. But in contact case, when you are given some function, at the moment, there is no means to convert this function into a vector field. Okay? Unless you choose one more data. So this one, together with contact form, choice of contact form, defines some vector field. I will write this way. This is contact Hamiltonian vector field. So let me give you the coordinate. So in canonical coordinate, let's say for autonomous functions, this is given by n j equal 1 dh dpj of ddqj. Maybe this is a little bit too. So let me just write down the equations. Qj dot is dh dpj and P J dot is negative dH dQj. And that's the classical Hamilton's equation. You can easily check if H is autonomous. This Hamiltonian is conserved under the flow because this is divergence-free vector field. Now, the contact Hamiltonian equations, this has this form. Qj dot is dH dPj. Pj dot is negative dH dQj. Okay. Minus Pj of dH dz. And then G dot equals H minus H plus P dH. Let me write. Okay, so what's here, as you can see, I mean, you can check the Hamiltonian is not conserved under this flow. Actually, it is not only conserved, you can check. So here is some observations. Under the flow of star, you can see dH dt ddt of H compose gamma t. Gamma is the flow of this. You can check this is negative H and dH dz of gamma t. Okay, and in more, okay. So what I'm trying to say is that is this right? Something doesn't look right. So I think it is right. Okay. So for example, H comes from cotangent bundle. If H does not depend on variable z, then the right-hand side is 0. So that goes back to this classical symplectic Hamiltonian dynamics. Otherwise, this sort of measures dissipation of this Hamiltonian. For example, if H, the derivative of H with respect to z is positive, this is always negative. So for example, in particular, if H, the derivative in the dH dz is, let's say, positive or negative, then this is always increasing. If this is positive, this Hamiltonian is decreasing in time. So this kind of smells like some kind of entropy behavior as you approach the thermodynamic equilibrium. And indeed, this was, pardon? Yeah, so what I'm saying is H is monotone. Okay, if if this is negative and this is always increasing, but okay, so this was kind of indication of compact Hamiltonian dynamics may have something to do with the thermodynamics, non-equilibrium thermodynamics. So this is the indications of the relationship between the compact Hamiltonian dynamics and thermodynamics, non-equilibrium thermodynamics. So this was the kind of starting point of my research in that direction. So now let's go back to the classical thermodynamics, first and second law of thermodynamics. So the first law, I just write one written form of first law, the most popular one. This is du equal TdS minus PdV. Okay. And more generally, there may be some other mole number related, is a DMI, so DNI of, what is the, maybe alpha I, okay, more generally for more variable chemical potentials. But this is the most popular one. U is energy and S is entropy, thermodynamic entropy. So let me write energy. S is thermodynamic entropy. And T is the temperature. T, pressure. V is the volume of a container. But this is only one representation of first law. You can also express this law in terms of entropy. So if I can rewrite this like by dividing by ds, so 1 over T du plus P over T dV. So this is entropy representation. And you can also write another way in terms of so-called Gibbs potentials. That is dg equal negative st dt plus v dp. And here G is the Gibbs potential, U minus or plus Just let me finish writing this. Plus PV minus ST, or the other way. So let me du, dg, dst, d minus st, okay. Minus st plus PV. This is Gibbs potentials. So there are many different ways of writing the first law. But so in that regard, something is, the one form is changing, but something is preserved. That what's preserved is this distribution, thermodynamic distribution. Under this transformation, these transformations, you can rewrite this, everything you move this to the left-hand side, regard this first law as the vanishing of one form. That's a contact form, okay? So under this coordinate change, although the forms are changing, but their kernels never change. So contact distribution, so the associated distributions are preserved. So in this regard, I would call that distribution thermodynamic distribution, thermodynamic contact distribution. So in thermodynamics, actually the fundamental object is not the way how the first law written, but this distribution is the something to make sure conserve. It's a covariant object. Okay? So that's the first law.
Can I ask you about?
Yes.
Okay. Without contact, suppose that you have the equilibrium situation.
Equilibrium, that's what I'm going to talk about now.
And then you have the contact and then the non-equilibrium situation.
Right. At the moment, what I did is I sort of defined what would be the non-equilibrium thermodynamic phase space.
Okay. In the sense of the first law,
Only first law is imposed. Okay. Now here comes the second law. So what does the second law do in the point of view of contact geometry? So here's the second law. So it's roughly saying the equilibrium state, thermodynamic equilibrium states maximize or minimize depending on the conventions. So let me write maximize the entropy, whatever that entropy means.
let me ask you about firstly, what is the maximization or minimization entropy? Is the contact geometry or something else? Or what is it? Geometric viewpoint. We have the.
So here's the, I think what your question is, what is the entropy?
Yeah,
What is the, right. So that's what I'm going to answer in this talk. So what we are going to maximize, okay? But that's what, so actually more precisely, this is the maximized entropy under the same, let's say, measurements or average of measurements of this random variable statistical parameters or variables. I think they most random variable state variables. Here is the next thing. What is the measurement? So that's the next thing we have to answer.
Law of thermodynamics. Let's say you are in a fixed system, fixed volume system, and you increase the pressure, this fixed volume, and you want the energy to increase. But according to that equation, the pressure increases, energy decreases because of the minus sign. I mean, how would you interpret that? Because if the pressure, let's say volume, temperature, entropy, everything is fixed. When you increase the pressure in the fixed system, then the energy should increase also. But according to that equation, energy.
Well, how can you increase pressure with fixing volume?
Change of I guess changing the.
You're thinking of some closed system, right? So if you fix the volume of container, I think this pressure, should be regarded some kind of average or macroscopic pressure that should be fixed. So volume, so I'm sort of, yeah. Yeah. Okay, so now here comes so basically the mathematical or the interpretation of thermodynamic equilibrium state, it should be something about special Legendrian submanifold with some constraint, okay, with some constraint, which I'm going to explain what that with some constraint. What I want to emphasize is that Legendrian submanifold. Every equilibrium state is a Legendrian submanifold. Okay? And the variation of this Legendrian submanifold can be regarded as some change of this equilibrium, thermodynamic equilibrium under the contact Hamiltonian flow. So I want to now explain how we can derive of this thermodynamics from the statistical mechanics. Roughly via averaging process. So we all know what average means as integration of function over some probability distribution. So let me introduce P. So let me start with the V. Okay. V is the statistical phase space. SPS. Statistical SPS. Okay. Statistical phase space, meaning that classical phase space of many body systems. Okay, so it is basically T cotangent bundle of R, let's say what, N particles, so R3N. N is not that N, so let me, yeah, N, I want. N is the number of particles. So in this talk, I'm going to ignore this collision effect. Okay, so I'm going to take this as the full phase space of a many-body system. And we know our classical phase space carries a natural measure. So let me write this mu n, the standard Liouville measure. So meaning that you take the so you regard T star of 3 R3N, and they look at the standard symplectic form, the standard symplectic form of cotangent bundle, and then mu n is just omega n to the how many? 3n. Okay, this is Liouville volume form. On this cotangent bundle, and it's the Liouville measure. That's okay. Okay, so and then let me write PV is the space of probability distributions. So in other words, the rho, the density such that positive density with this V of rho is identically 1. Okay? That's just the probability distribution. And this is some affine space. In infinite dimensional affine space, I basically want to do some kind of field theory on this probability distributions. Spaced out. That's what actually statistical mechanics physicists do. So then we want to consider its cotangent bundle. So this is going to be the field space. Okay, and then for each functions, let's say f on this statistical phase space, you can regard this as a random variable by considering V as this probability or measure space. And we define its partition or average. So define f by the functions of PV going to R, so that you define of rho is just the integral of rho f. Sorry, V. So this is kind of linear function. Because VB is not a linear space, but anyway, some affine functions. So Okay. I mean, by the general fact, in Hamiltonian dynamics, whenever you look at functions, so let's say you consider any cotangent bundle, okay? And the functions, the set, let's say you consider several functions, f1, let's say fk, defined on the base. Okay? Yes. Maybe f is maybe confusing. Maybe gk, r. And you pull back, it's pullback, so it's their pullback. Let me write g I tilde is a pullback of gi. Pi is the canonical projections. Okay? And they are Poisson commute.
So what is the n? N is the two-dimensional.
Or any smooth manifold. Sorry, too many n here. But let me know.
And then is it boundary? Is it close or is it boundary?
Smooth, no boundary. Yeah. Okay. And they are Poisson commute. So therefore, their flows define some action. So their flows define an k action on this cotangent bundle. And in fact, they're moment map, and furthermore, their moment map, it's moment map. It's nothing but, so moment map is J, let's say F or G, G, that is from T star n to Rn, is nothing but, so this is given by J, thank you. Okay. So this one, alpha 1, oh no, alpha or QP. I think it is either just average. So G, what am I doing? Oh yeah, I'm giving function G. So G 1Q, G and Q maybe. Okay. So now let's apply this to this infinity dimensional situation. applying this, let's say this function, let's say f1, let's say fk, where fi is random variable on D. And the moment map is a precise measurement. So we have moment map, let me write this way, of probability the rho beta. So rho beta is an element, is cotangent bundle of this probability distributions. Depends only on rho, that is exactly measurement. So this one it's V F1 rho V F K rho. So second law of this thermodynamics can be said, we want to maximize some function, which I will talk shortly, in these preimages of this moment map. So in summary, the preimage of some measurements, let me write measurement is, let's say, so M1, MK is nothing but the space of the space of this rho beta with the same measurement. Of these k random variables. And furthermore, these are abelian, but Rn action is abelian. So now we can quotient them out. This is symplectic reduction. That is, I'm going to write this F modulo that isotrope RK action, which I'm going to call the mesoscope reduced space, which I'm writing this M F of fixed measurement. This carries a natural symplectic form again. So carries natural symplectic form. So this is a so-called Marsden Weinstein reduced space, but this is infinite dimensions. Now you vary the measurement. So let's consider, now form the union of F and measurement here, RK, of M, F, M, as a fibration over this R K. This is a measurement space. Now here is a natural function, Shannon's this information entropy. Function enters. So all the other this average is a linear function, fi, in terms of this variable. But there is a very particular random variable that does not depend on this phase space. It's a purely intrinsic function defined on the space of probabilities. Actually, I would call relative information entropy. So you recall V of mu, it has natural measure space. So whenever this is, in this situation, we define so-called relative information entropy, or sometimes called Kullback-Leibler divergence. It's defined in this way. So let me write S. Rho is going to be negative rho, okay, or rather Nicodim derivative of d rho, d mu of mu. Okay? So maybe I'll put the negative. Now this is, again, a function defined on the probability distribution space. So this is purely defined on the probability distribution space. So we want to maximize. So the second law, oh, by the way, this function itself depends only on the configuration variable. So it commutes with all the other variables. So by the general principle of symplectic reduction, this function goes down to that reduced space. So we maximize or minimize this entropy inside on this MF at each given fiber.
I'm sorry, what is the, understand your point, what is the maximum minimize on the which space, n space or which one?
Oh, on the this in terms of this probability distribution, we want to find the best probability distribution which maximizes that entropy.
Where the probability distribution located in which space?
Oh, our classical phase space, the statistical phase space.
You have the Ruby form that's the control, that's a benefit of large n.
No, V.
Unless the basic setting is okay. Sorry, sir. What is the maximize, the minimize of the surface?
Maximize S on here, on here. So what here means, you look at all the probability distribution with the same measurements. Among them, you want to maximize this entropy functions. So let me draw this is the typical situation in symplectic geometry or contact geometry. No, rho is a probability distribution. You can think of a function because I have this reliable measure in the background. Okay.
Kind of reminds you that minus 5 is
Huh? Yeah, so I just finished with this one, okay? So the situation here is a generating function. So what is the generating function? We have this situation. Let me write S and M, F, and here is function R, okay? And here is a fibration of RK. Whenever you are given this situation, there is a canonical way of producing Lagrangian or Legendrian submanifold. So that's the situation. I'm going to write this, let's say F of general fibration E to N to R. And whenever you are given, this is Morse family. Suppose this is Morse family. You look at the family of Morse functions over this parameter space N. This will give rise canonically some Lagrangian submanifold inside cotangent bundle N or Legendrian submanifold LF F in one bundle Lagrangian and Legendrian. So by applying this critical point, family critical point theory. So in other words, you fix each fiber, you look at the maximum, find the critical point of F, and then you look at, okay. So let me just finish. The way how this Lagrangian submanifold goes like this. So we define sigma F. This is a subset in E. It's the vertical critical set. You can see the dimension of sigma F is precisely the same as dimension of M. So it's because I made the vertical derivative vanishes, we have a horizontal derivative remain. So you look at the horizontal derivative of this F, regarded as a map from sigma F to cotangent bundle of R. The image is a Lagrangian submanifold. The AF is nothing but image of BHF. And if you include the value of function, this becomes Legendrian submanifold in the one-jet bundle. So my last statement is that thermodynamic equilibrium can be written, generated by applying this general construction in symplectic geometry. Okay? So I'll stop here.